Hello everyone and welcome back. What if the biggest threat to a drone isn't a crash, but its own vibrations? Every spinning propeller creates forces that travel through the drone frame. If those forces match one of the frame natural frequencies, resonance can occur. And when resonance happens, so vibrations can become so large that they affect stability, damage electronics, loosen fasteners, or even cause structural failure. So today we are going to test a drone frame in ANSYS and answer one question. Can this drone survive high-speed flight? So before running any simulation, as you can see now we are moving one of the mode shape for this quadcopter. And before running any simulation, let's understand the problem first. So every structure has natural frequencies. Think of a tuning fork, strike it once, and it vibrates at specific frequencies. So a drone frame behaves the same way. Meanwhile, the motors and propeller generates periodic excitation forces. So if the propeller excitation frequency gets close to a natural frequency of the frame, resonance can occur. So this is something aerospace and drone engineers actively try to avoid. So our goal today is simple. Find the natural frequencies of the drone frame, visualize the vibration modes like the one we are seeing right now on the screen, compare them with expected motor excitation frequencies, and determine whether resonance is likely to happen or not. So let's start with the simulations. So here we are using a quadcopter frame model, and the frame consists of a central body, 4 arms, and motor mounting location, which is at the end of each arm of this. So for example, we'll assume the frame is manufactured from PLA material. In our case here, it could be with other materials, it depends. So in case you are having on drone and you want to test it, so you have to specify the relevant material. In my case, it's PLA material, which is some sort of elastomer. The geometry is imported into ANSYS Mechanical and checked for defects before meshing. I already prepared the geometry to do the simulation. So our focus now to answer the question actually can this drone survive the high speed flights? So let's see that together. So first of all, actually the material properties we are using include three important parameters, which they are the density, Young's modulus, and Poisson ratio. These properties directly affect stiffness and mass, which are two key key factors controlling natural frequencies. A stiffer structural generally produces higher natural frequencies. A heavier structure generally produces lower natural frequency. So actually, and now while we are preparing this a quadcopter for simulation and also do the modal analysis using ANSYS, we can see from the material section there that I choose PLA, just to see together what I did define here. So the Young's modulus for this material is around 3500 megapascal. It has a Poisson ratio of 0.36 and so on. And the density we have around 1240 kilogram per meter cube. For this material that we'll use for the overall quadcopter frame, as we can see, I did generate simply automatic mesh, which is it seems coarse. And this simulation, of course, you can do a sensitive mesh study on this mesh in this study, in case you wanted to study if that will affect hugely the results at the end. In this video, we are just for learning purposes, we are using just a default size on this quadcopter frame. So after that, you go to the setup, and here actually where's most engineers and YouTuber actually when do such studies make mistake actually. Depending in ANSYS actually, you have to define always a support to prevent that your structure falling out. But while you are doing a model analysis and specifically like for quadcopters and drones, actually defining like supports or displacement or remote displacement that could be in most cases like make the results like wrong. In some cases they could be like near to the reality, but in this video I will like recommend to you and give you a tip and trick actually that you have to use in order to get the right results at the end. And this is actually by not defining any support for your structure. Of course, we are talking here about like a drone, which is like should be flight on the air. So if we are like defining a support, even it's like not like so rigid, even if it's like deformable, it's at the end a support. But in the reality, the drone in the air, it's like more flexible. It's near like to have no support at the end. So that's why in my study here, as you can see my displacement, I already suppressed them. So I have no support in my structure. And that's mean actually I have to expect to get on the first mode shape some rigid body motion, which the result should be like be zero or too much like near to zero. But this mode shape, I can actually simply ignore them and search for the first one mode shape with like a real value. So in your drone structure or in this like quadcopter, I will not define any support. All what I have to do actually is to define like how much like mode actually I want to request from ANSYS. So as you can see here from the max modes to find, usually by default it has like 6, which they are like the most like representative like mode shapes, which define the on the all the directions coordinate system that we have and the rotation direction. But in my case, and because I already know that I will have like some rigid body motions and I will have some mode shape that have like nearly zero as a frequency, so I did define a 20 like mode shapes to be founded by ANSYS as a first like start like simulation for my model. So I will define 20. In your case, you can define 20 or more. It depends. But first of all, let's try this with 20 modes. I already like solved this. And actually, I got the following. If you click on the solution, I'm gonna like delete this and I will request all the results like again. One moment, so we delete this. By clicking on the solution, you will get this like list, which has like 20 cells, because we already defined like that we need 20. And as I expected, actually the first 6 mode shapes, the first 4 they are like 0 exactly, and the 5 and 6 they are like nearly 0. So in this case this is like very like expected to have, because I don't have any support in my model. So I ignore these first 6 like mode shapes, and I see here on the mode shape 7 that I have 47, which is like a realistic value. In that case, I will like mark all these values that I have here and right click and create mode shapes. After you do this, you will get them on the under the solution. You just click on it, right click and evaluate all results. Now you can like jump to each one of them and see like how like each mode shapes of them like look like. Like if you can like play them, you can see that the first mode shapes I will have this like a form of like mode shape. The second one, it will be completely like bending. The third, it will be like some twisting, like you can see it on the arms, and so on. Of course, like we have like a lot of mode shape that could be occurs at the end. It depends like on which frequencies actually this quadcopter operate. So we have to compare our result to that operation like range and see where resonance could be happen. So in order to do that, all what you have to do actually to make it like easy, I will like copy this, sorry, I will copy these values I will copy all these values to an Excel file. So let's copy them to Excel file. They are like a frequency. So if we wanted to know these values in terms of RPM, so we have to multiply these values by 60. So we multiply these values by 60. And as you can see, these are, let's name them RPM at the end. So this is our RPMs. That's mean like when we operate at one of these RPM, we have to expect resonance at that RPM with the relevant mode shape that we can see like clearly from ANSYS there. So our quadcopter actually operate between 4,000 to 10,000, actually depending on the speed that we want. So if we compare these values to the values that we have, I can see that the 4,000 actually it lies between between this mode shape and this mode shape. It could be like better if we run the quadcopter actually exactly in between, so we have like some space. So it will be like I see here like having like 4,500 RPM. It will be a good start, so we prevent any resonance, because always you have to take some safety factor. In this case, I can see here that I have many resonance that occur by 6,300, 6,500, 6,800. They are all near each other. So we have to prevent any speed at these RPMs, like between 6,000 to 7,500. I would recommend to not use any like speed at this like range. So after that, I can see that at 10,000, I have 10,000, 9,500. So I will recommend actually, and because we have no mass now yet on our structure, so I will recommend to use like under 9,000 RPM. So it will be like 4,500, and we can use it from like 8,000 or 8,500 to 9,000 RPM safely for our structure. In case we want to use one of these like RPM, so we have to do some optimization to our structure. And in this case, actually, if you wanna if the frequencies are too close, so engineers may need like to increase stiffness, reduce mass, change geometry, or modify operating speed ranges. So this process is commonly used in aerospace, automotive, and UAV like designs. So suppose resonance is detected, what can we do? So one option is increasing arm stiffness, or another is adding reinforcement ribs, or we could like also redesign the frame geometry to shift natural frequencies away from motor excitation frequencies. So even small design changes can significantly like improve vibration performance. Now, as a conclusion for our study, today we use like ANSYS Modal Analysis to investigate whether a drone frame could experience resonance during operation. We identified the natural frequencies, visualized the vibration modes, and compare them with expected motor excitation frequencies. This is exactly the type of analysis engineers perform before building real UAV systems. So if you found these simulations and want helpful and want more ANSYS projects involving drones, aerospace structures, CFD, and finite element analysis, subscribe to that channel and let me know what you would like to see next. Thanks for watching, and I will see you in the next video.